Hello everyone, I'm Shachi. I'm from Stony Brook University and I'll be talking about our work titled SGXPecial, Specializing SGX Interfaces Against Code Reuse Attacks. We'll start by talking about code reuse attacks, then about interfaces in general in Intel's SGX, and finally about our work, which is titled SGXPecial. This is what the outline would look like as I discussed. So shall we begin? Let's start with a quick 101 on code reuse attacks. The adversary can reuse benign code from the processor's address space. Say this is a control flow graph of an application. It moves from function to function. Now, when this application wants to interact with the operating system, it uses shared libraries, which does this on the application's behalf. Now, say we had a hidden bug somewhere in the application and the attacker was able to exploit this. Once exploited, the attacker looks for gadgets in the application. These gadgets could be full function or instruction sequences. When found, these gadgets are chained together to achieve arbitrary code execution. Now, when this attacker wants to interact with the operating system, which it would in order to do any substantial damage, the gadgets that are used are from the shared library itself. Now, one way to prevent these attacks is by means of application debloating, where anything that is not needed by the application gets removed from the application's access and from the attackers as well. The application behaves perfectly normal, but the attacker now has restricted capabilities. For example, here we have this application which uses the function foo from the shared library. Without any attack surface reduction or application debloating in place, the attacker can also use another function, say bar from the same library. While with when the attack surface is reduced, the function bar is no longer there. And the attacker, when they try to use it, it does not succeed. Now, this reduction as attack surface could be at many different levels, a full function, as is the example here, or maybe in for smaller instruction sequences. As we saw in the previous slide, not all functions can be removed by function debloating. Case in point, the function foo there. We thus further extend the impact of debloating by restricting arguments that are passed to these critical functions which cannot be reduced. Here the application, we have two instances of function foo being called. Even with function debloating, an attacker's call to the same function foo would be successful. With argument specialization though, function foo is specialized. It's specialized to only accept the arguments from the original code base. In this case, the integers 1 and 2. When now this attacker calls foo with any other arguments, the attack fails. Now, before we talk about the rest of the work, let's try to gaze into control flow integrity. And how it is an important tool in preventing against code reuse attacks. In a nutshell, CFI is runtime enforcement against control flow hijacking. It works by extracting the control flow graph or finding the valid sets of targets for each flow. At runtime, CFI ensures that every control flow transfer sticks to the extracted policies. For example, let's bring back the application from the first few slides. The control transfer rules would look something like this. Main function can go to function 1 and to function 2. 1 can move to 3 and 4, and so on and so forth. In case of a code reuse attack, though, the control flow transfer does not look like this. An attacker, when they try to hijack the control flow and make a transfer from function 5 to function 4, this rule violates the set of CFI extracted policies, and the attack does not succeed. So what happens now? As we understand that the attackers are now restricted to specific control flows. A function can have multiple invocation points within an application, and not all of them would be equally protected by CFI laws. Again, bringing back the same application, now say we've added these two instances of execv system call to it. Now, execv gives the ability to execute any command, and thus in Linux is one of the most security critical system calls. Here it is important to mention that there are two different kinds of flow transfers here. The solid lines are the direct flow transfers, while the dashed ones are indirect flow transfers. Of the two exec we call, the right one has direct control flow transfers all throughout. The CFI rules are pretty strict and straightforward there. While for the one on the left, there is an indirect control flow transfer. There's an attacker who can use some vulnerability within this application, and because of the lack of fine-grained CFI rules, they can reach this function. So although what I'm trying to explain is, although they are the same function execv at two different call sites, the left one is more likely to be used by an attacker than the right one. The specialization policies like ours, which find it important to protect one over the other. I'll not talk about Intel SGX with a focus on the SGX interfaces, which we specialize in the next part of the talk. So Intel SGX is a trusted execution environment where the trusted region called enclave is protected from any malicious actors. The data and code from the enclave lives in a protected memory within the application, and then enclave entries and exits require special instructions called EENTER and EEXIT. The enclave region in itself consists of the code, data, and the control structures that make up the enclave. The Intel's SGX SDK and our attack surface. Intel's SGX SDK is the most popular tool for building SGX applications. The source and tools from the SDK are compiled, and they create a runtime environment where the enclave and the application code exist in the same memory space. They interact with each other through a set of dynamic libraries, one on each side of the trust boundary. We have the Trusted Runtime System, or the TRTS, and the untrusted runtime system, the URTS. TRTS is on the trusted side, it's on the enclave side, while the URTS is on the application side. Now, when say the application wants to execute an in-enclave trusted functionality, it makes a function called, special function called an eCall, which is captured by the URTS, sent to the TRTS, which actually calls the in-enclave function which the application intended. Similarly, when the enclave wants to use a functionality from outside, say it wants to call a system call, it makes a function call which is called an O-call. It follows the same path, just in the opposite direction. So this interface between the trusted and the untrusted systems, which consist of the TRTS and URTS, is the specific attack surface that we are targeting, and a lot of attackers have been targeting as well. Now we talk about code reuse attacks in Intel's SGX. First, with the standard SGX threat model, where everything which is outside the enclave is untrusted. The operating system loads the enclave in the memory, but it is in encrypted state, so none of the untrusted members can really scan through or read what is going on inside the enclave memory. This way, SGX provides confidentiality and integrity to the enclave. But even then, as has been shown, and we will see in the next few slides, the attackers have been able to launch code reuse attacks against the enclaves. One such attack is called the guard's dilemma. It is basically a return-oriented programming, or a ROP attack, that uses gadgets or smaller instruction sequences from the runtime libraries that the Intel SDK generates. So, although the enclave memory cannot be read, the TRTS, the Trusted Runtime Systems, is same across all the systems, and thus we have this attack scenario. So in this attack, the malicious host exploits an in-enclave bug to divert control flow to one of the functions in the Trusted Runtime System. The function that it redirects to is the one that restores state when the enclave is entered. The attacker then introduces a fake or a counterfeit state into the enclave stack and uses gadgets from TRTS itself to restore enclave state while this function is being executed. In absence of something like backward CFI, which takes care of what are the functions that execute and make sure that it's the same functions that execute in the reverse order as well, the enclave cannot really detect that there has been some change in what it was executing versus what's actually executing, and this change in control flow gets undetected. Now we talk about the attack surface from the other end. That is one that encounters the SGX threat model, which is when the enclave itself is malicious. So Intel sometime back released a statement that says that Intel SGX does not guarantee that the code executed in the enclave is from a trusted source. They make sure that it is executed within a trusted environment, but the source of that code cannot really be trusted. In the recent times, a number of web application developers, they use enclaves which are from third-party sources. But we have to understand, enclaves are black boxes. By virtue of the protection mechanism, or the operating system and the application, they cannot really look inside the enclave encrypted memories. We do not really know what exactly is going on there if it's a third-party enclave. The enclave could come from an untrusted source and can contain malicious code, and the current set of malware detection tools, they all fail while it comes to enclave just because the scanning is not really allowed with how currently SGX works. So SGX ROP is actually one of the first published code reuse attacks that consider a malicious enclave that uses, so SGX ROP uses Intel's transactional memory, which is TSS, to look for gadgets in the host application. The reads and writes that are done through TSX are atomic, and any error in reading through inaccessible memory is aborted and rolled back instead of really raising an exception or giving a segmentation fault. This way, the enclave, which is malicious, uses read and write capabilities to read gadgets from the application code and write these malicious payloads to the application's data memory. The injection step, the third one on the right, is used to steer control to a fake stack via means of ROP chains, which are again injected by the malicious enclave itself. So to summarize the attack surface, SGX enclaves, they create these two runtime systems, the untrusted runtime system, which is loaded and used by the host application, and the trusted runtime system, which is inside the enclave. These two create this interface over which the trusted and the untrusted components communicate. Every time the host application wants to call an in-enclave function, it makes an eCall, and this eCall is transferred from the untrusted runtime system to the trusted one. When a function running inside the enclave wants to temporarily call an outside function, say a system call, this kind of call from inside the enclave to outside is called an OCall. This OCall is made by the TRTS and received by the untrusted runtime system. This red box is the one that performs all the communication in and out of the enclave. We display the attacks here that strengthens the idea that interface specialization from trusted execution environments like SGX is critical and a relevant problem. As we can see here, there are attacks like DarkROP, T-Rex, and Guard's Dilemma, the one we discussed, which where they consider the host application as malicious or vulnerable or untrusted, while there are other ones which are SGX ROP and SGX Jail on the right side, where the enclave itself is the malicious one. Now, we argue that we need to get these problems resolved for trusted environments like SGX to be widely adopted for real-world applications. So now that we've talked about everything, we finally start talking about our work, which is SGXPecial. In a nutshell, SGXPecial specializes SGX interfaces according to the needs of individual applications. The source and the Intel SDK are input to a compiled tool chain extended with SGXPecial to create this application and enclave that have a very strict interface. The URTS and the TRTS only allows specific functions to be accessed from within from the enclave and from the application. Any attempt to use other functions which were not part of this original specialized runtime systems, it leads to the function calls being blocked. Now, to perform this specialization, SGXPecial does 3 different levels of specialization, and in the next few slides, we will look at each one of them in detail. So the first level of specialization is the basic one, which is called the function level specialization. It is akin to the function level debloating in applications, but with a slight difference that I'll discuss. So SGXPecial analyzes the application source to create interfaces which are specialized to its need. So for example, the application uses the function that creates and initializes SGX enclaves, but it might not use a function which is used to get the SGX's metadata. However, because this function might be used for the actual enclave management and for bookkeeping purposes, functions, they cannot really be entirely removed from the application's address space, so they cannot be erased. For instance, on the other side, from the TRTS side, there's a function called do eGetKey, which is used to extract cryptographic keys in SGX. And while an application would rarely use this, the enclave needs it because it needs to perform the cryptographic functions. So we specialize the runtime systems in a way that the functions are only executed if they're part of the input source, and any other functions, any other function call is blocked, even though the functions really still exist in the memory, only that they cannot be called from the core enclave code or from the application code. Next, SGXPecial performs context-sensitive argument specialization as the next level after function-based specialization. The core here is to perform analysis to extract and neutralize static arguments to functions. Let's take, for instance, eCalls. The techniques I'm describing apply to all function calls. I'll just be talking about eCalls here. So the eCalls are made using a generic interface function called eCall. The actual trusted function to be called is identified using an index that is passed as argument to this function. Thus, to call the function foo here inside the enclave, the argument passed has the index 1. While to call the function baz, the index value passed is 3. Now, as an attacker, they can, if the host is malicious or vulnerable, they can exploit this vulnerability and change the arguments inside the in the eCall and change the index from 1 to 2, as you can see here. They can make the same call site, which was the same call site to eCall, now call to another function, which is function bar inside. So thus an attacker, although they did not really make any changes to the enclave, they were able to alter the control flow of the application within the enclave itself. What SGXPecial does is that it identifies this and creates variants of eCall functions, each catered to specific call sites. Similarly, the eCall functions which are inside in the trusted domain called within the do eCall also go through the same thing. Now, the eCall function inside the enclave, as I said, also have 3 specialized variants here. Now, even if the attacker they do try to manipulate the application and manipulate the function arguments and try to make another call, because this call is now specialized to only go through the chain which calls the function foo, the attack can now be prevented. So finally, SGXPecial performs narrow scope type signature based filtering. As host applications cannot really read or write through enclave memory, the arguments to various eCall functions are marshaled into a structure and passed into the enclave. Thus, an eCall function expects a pointer to a structure with the arguments, and the arguments are written to it before being passed. Now, taking this generic implementation, and the attackers can create arbitrary structures which have malicious data that gets copied into the enclave memory through this process. SGXPecial performs type verification, a narrow scope one for that, for arguments before they get marshaled into generic structures. This way, any extra arguments are never added to the structure that is created, and they're never copied into the enclave memory. Now, to evaluate the performance of SGXPecial, we tested it with 7 sample applications and 4 real-world applications that use SGX, including Embed TLS SGX, the TLS stack developed with SGX. We have SQLite, we have SGX SSL, and file encryption application called SGX CryptoFile. We test them for a variety of criteria, including how many functions can be restricted and the number of arguments to functions that can be statically found. The results look something like this. Each color bar here represents an application, while the y-axis is the percentage starting from 0. The first group shows the percentage of URTS, or the untrusted runtime system functions there which are used by the application. As we can see, SQLite is the one that uses the maximum, about 45% of the functions. So there are 55% of those functions which are never used, which can be readily removed. So the step 1 of function level debloating removes the available functions by a great margin. This results, or the margin, is even greater when we talk about the next group, which is the percentage of TRTS, or the trusted runtime functions, which are used, where none of the applications that we tested used more than 12% of the available trusted functions. So we have this huge scope, number of functions which are there, which are not going to be used by the applications, which can directly be removed. The next 2 groups, we show the percentage of functions that can be statically found in eCalls and in OCalls. We see that around 40% of the arguments can be statically identified for each of the applications. This argument level specialization also reduces the attack surface available. We'll now bring back the 2 attacks that we talked about earlier and see how SGXPecial performs against them. We start with Guard's Dilemma. The rob attack from the application that uses gadgets from TRTS. The malicious application exploits a bug in the enclave and calls this function, which is ASM ORET, the function that is used to handle returns from OCalls, which in turn calls this function called xreg restore to restore the state of execution. At this point, the counterfeit state, which was injected by the attacker, that itself gets loaded, and the attacker now has control of the enclave. What SGXPecial did was that it identified that the original function, which is the ASM ORET itself, is never directly called by the application. Hence, it can be removed from the trusted runtime system or from the TRTS being accessed from the enclave altogether. Thus, the whole attack gets blocked because the enclave code does not really have access to ASM ORET or the core function that it started with itself. From the malicious enclave endpoint, we talked about SGX rob that uses Intel TSX to look for gadgets in the host application. The functions read and writes are OCalls, and they are identified and analyzed by SGXPecial itself. And if the application does not use these functions, they're not allowed to be executed while you're inside the enclave. Also, SGXPecial performs argument-based specialization as well. So if the functions are indeed required, this taking away the ability to read and write arbitrary memory from them. Now, to conclude my talk today, we presented SGXPecial that modifies Intel SGX SDK to generate interfaces specialized to the current application and the enclave. SGXPecial performs function level, argument level, and type-based specialization. We tested SGXPecial with sample and with real-world applications and show that code reuse exploits present in the wild can indeed be prevented by integrating SGXPecial with Intel's SGX SDK. Thank you, and I'll be happy to answer any questions.